So last time we looked at geometric series and we determined that geometric series converged to a number if and only if the absolute value of r, what we call the ratio, was less than 1. And if it did converge, then we were actually able to find what it converged to. In particular, we derived a statement that said it was a over 1 minus r. Well, a geometric series is a very special kind of series in that we actually can not only determine whether or not it converges, but if it does, we can tell you what it converges to. Now, the series that we're going to look at, we're simply going to ask the question, does it converge or not? And oftentimes, we're not going to be able to tell you, even if we know it converges, what number it converges to. So the first test that we're going to look at is called the integral test. And the integral test, which is right here, has the following statement. If a function f is continuous, positive, and decreasing on 1 to infinity, then if the improper integral from 1 to infinity of f of x dx is convergent, then the series a sub n is convergent. Now, what's a sub n? Well, a sub n is just the function that we're looking at evaluated at n. So the integral test gives us a way to figure out whether or not this series converges by looking at this integral. If this integral converges, then so does that series. Now, remember, we can only use the integral test on functions that are continuous, positive, and decreasing. Okay, so let's look at how we might use the integral test. To begin with, I'm going to look at this series right here in running from 1 to infinity, 1 over n. So that series is what? 1 plus a half plus a third plus a quarter plus dot, dot, dot. So that's my series. What's my function? Well, since a sub n is 1 over n, my function that I'm going to look at is 1 over x. Now, what should you notice? You should notice that 1 over x is, in fact, positive and decreasing on 1 to infinity. Okay, which means I can apply the integral test. So I'm going to look at f of x equal 1 over x, and I'm going to look at the integral from 1 to infinity of f of x. So that is the integral from 1 to infinity of 1 over x dx. Well, the integral of 1 over x dx, you know to be natural log absolute value of x. And I'm going to plug that evaluated between 1 and infinity. That's an improper integral, so I plug in b at the top. Ln b minus ln 1. Of course, ln 1 is 0. And so I end up taking the limit as b tends to infinity of ln b. Well, as b tends to infinity, ln b tends to infinity. So what does that tell me? That improper integral does what? It diverges. Well, the integral test then tells me that this series, 1 over n, diverges. All right, so in fact, that series diverges. In other words, if you sum up all the entries, it just gets bigger and bigger. By the way, as it turns out, this series is so important that it has a special name. It's called the harmonic series. All right, now let's apply. Now, you will notice that, well, let's just say that series diverges. Now let's do another example. Okay, so here's the example of a series. Notice I choose n to start at 2 to infinity of what? 1 over n log n. Okay, that is a continuous positive decreasing function on, well, in this case, it's on 2 to infinity. Actually, it doesn't really matter where you start. If you start at 1 to infinity, you look at the integral from 1 to infinity. If you start at 2 to infinity, you look at the integral from 2 to infinity. And by the way, in this case, it's important I start at 2 because if I were to start at 1, natural log of 1, of course, is 0, and that thing would be undefined. And that wouldn't be a proper series. All right, so I'm trying to figure out whether or not this converges. How are we going to figure it out? Well, I'm going to look at this function, 1 over x dx, right? Everywhere I see an n, I replace it with x. There's my function. It's going to be on the set 2 to infinity. I integrate from 2 to infinity of 1 over x ln x. And I'm missing a dx. All right, so how do I integrate that? Well, I integrate that by what? U equal ln x. And then du is 1 over x dx. And this becomes the integral of 1 over u du. Notice I drop my limits until I'm talking x again. So, of course, 1 over u du is natural log absolute value of u, but u is ln x. So you get natural log absolute value of ln x, and then you're going to evaluate that between 2 and infinity. Well, that's an improper integral, so that's the limit as b tends to infinity of, plug in b, ln b, minus ln 2. Now, the only thing important about ln 2 is that it's a number. Because as b tends to infinity, ln b, well, ln b goes to infinity, and ln of something that goes to infinity also goes to infinity. What do I conclude? That improper integral diverges. What does the integral test tell me? That if this diverges, then that series diverges. So I conclude that this series diverges. In other words, I don't get a number out of that either. Now, let's look at a whole series of functions. The summation n running from 1 to infinity of 1 over n to the p. And my only assumption on p is that it is greater than 1. Now, if it's equal to 1, I'd like to remind you that when p equals 1, we're back up here in this case. That's 1 over n to the p, where p is equal to 1. So we've already decided that that series does what? Diverges, and what is it called? The harmonic series. All right, so now let's look at these other ones where p is greater than 1. Well, I'm going to look at f of x equal 1 over x to the p again. Exactly this function, except where I see an n, I stick in an x. And now, right now, I'm going to assume p is greater than 1. What is that? Well, the important thing is that that is a continuous positive decreasing function on, but in this case, it's 2 to infinity. So that means that I can use the integral test. So what am I going to do? I'm going to look at this improper integral, and actually it's not 2 to infinity. This is going to be 1 to infinity, right? So I go 1 to infinity here, and I integrate what? 1 over x to the p, which, by the way, is x to the minus p. How do you integrate x to the minus p? Well, it's x to the minus p plus 1, that's this, over minus p plus 1. I've just reversed the order there, right? So the integral of this is, in fact, this, and I evaluate it between 1 and infinity. Now, that's an improper integral, so I take the limit as b tends to infinity of, and I plug in b to the 1 minus p over 1 minus p, subtract, and then I plug in b equals 1. So there is 1 over 1 minus p. All right, now what's the point? The point is p is greater than 1. But if p is greater than 1, then 1 minus p is less than 0. In other words, this exponent is negative. Now, if that exponent is negative, then it's b to a negative power. And if it's b to a negative power, as b tends to infinity, that goes to 0. Hence, this term goes to 0. And my answer is simply minus 1 over 1 minus p. What's the point? The point is that that improper integral converges. But the integral test says that if this improper integral converges, then this series, summation n running from 1 to infinity of n to the p, where p is greater than 1, also does what? Converges. So what have I done? I've proven that this series, 1 over n to the p, if p is greater than 1, always does what? Converges. By the way, we have a special name for this set of series, 1 over n to the p. It's called a p series. Get it? P is my exponent. So the summation 1 over n to the p, p greater than 1, according to the integral test, does what? Converges. Okay, now, you're going to notice I'm telling you it converges. You might ask yourself, okay, so if it converges, I get a number when I sum this up. What number do I get? And you know what? For certain p's, I might be able to tell you, but for other p's, neither I nor Mathematica can tell you what it converges to. All I know is it converges. And that's all the integral test does for you. It simply tells you, does it converge or does it diverge? If it converges, it doesn't tell you what number it converges to. All right, now I'm going to look at the same series.